Google's latest quantum processor has accomplished something that seems almost unbelievable. In less than 5 minutes, it completed a calculation that experts estimate would take today's fastest classical supercomputers an unimaginable amount of time, far longer than the current age of the universe. The numbers are so enormous that they almost lose their meaning, making this achievement feel more like science fiction than reality. The processor, known as Willow, is being celebrated as a major leap forward in quantum computing. But beyond the impressive performance lies a far more intriguing question. How can such a small chip solve a problem that appears impossible for even the world's most powerful conventional computers? Some physicists believe the answer may not simply be greater speed. Instead, it could reveal something profound about the nature of reality itself. Unlike traditional computers that process information using bits represented as either 0 or 1, quantum computers rely on quantum bits, or qubits. These qubits obey the unusual rules of quantum mechanics. Rather than existing in only one state, they can occupy multiple states simultaneously through a phenomenon known as superposition. When qubits become linked through quantum entanglement, they behave as a connected system, allowing a quantum processor to explore an enormous number of possible solutions at the same time. This unique behavior is what makes Willow's recent accomplishment so remarkable. Engineers challenged the processor with a complex random circuit sampling problem, a benchmark specifically designed to push quantum hardware to its limits. The task is intentionally difficult because the number of possible outcomes grows at an extraordinary rate. For a classical supercomputer, simulating every possibility becomes practically impossible as complexity increases. Yet Willow completed the challenge in only a few minutes. The result has renewed discussions about quantum supremacy, the point where a quantum computer performs a calculation beyond the practical capabilities of any classical machine. Google first claimed quantum supremacy several years ago with its Sycamore processor. But many researchers argued that improved classical algorithms reduced the significance of that milestone. Willow's achievement feels far more convincing because the performance gap has become dramatically larger. Instead of a modest advantage, the difference now spans a scale almost impossible to comprehend. Still, the real mystery is not simply how quickly the calculation finished. The deeper question is what a quantum computer is actually doing while it performs such extraordinary computations. Understanding that question leads directly into one of the most fascinating debates in modern physics. Quantum mechanics has challenged our intuition for more than a century. According to the theory, particles do not always exist in a single definite state. Before measurement, they are described by a combination of many possible outcomes. Only when observed does one particular result become apparent. Scientists agree on the mathematics behind quantum mechanics, but they continue to debate what those equations actually mean. One interpretation treats these possibilities as mathematical probabilities that help predict experimental results. According to this view, only one physical reality exists, and the wave function simply describes our uncertainty until a measurement is made. Another interpretation presents a far more astonishing possibility. Known as the many worlds interpretation, it proposes that every possible outcome actually occurs. Instead of one possibility replacing another, reality continuously branches into countless parallel versions. Whenever a quantum event takes place, every possible result exists in its own separate branch of the universe. Imagine flipping a coin. In everyday life, you see either heads or tails. Under the many worlds interpretation, both outcomes occur, but in different branches of reality. Each version continues independently, completely unaware of the others. Now imagine applying this concept to a quantum computer. Instead of testing one possibility after another like a classical machine, a quantum processor manipulates many possible states simultaneously. Some physicists have suggested that these parallel possibilities might correspond to genuine branches of reality interacting through quantum interference before producing the final answer we observe. Although this idea sounds extraordinary, it has been seriously discussed by respected physicists for decades. Willow's latest achievement has simply brought the conversation back into the spotlight. If a tiny quantum processor can solve a problem that appears unreachable for classical supercomputers, perhaps the explanation involves more than clever engineering. Perhaps quantum computation is revealing something fundamental about how the universe itself operates. Imagine asking one person to solve a puzzle so enormous that it would take countless lifetimes to finish. The task would be hopeless. Now imagine that millions, or even infinitely many, versions of that same person each solve a tiny piece of the puzzle simultaneously. If those partial solutions could somehow combine into one final answer, the impossible suddenly becomes achievable.